Hey guys, and welcome back to another episode of the data series. Today I hope to explain to you guys gradient descent, which is a very fundamental algorithm in the world of machine learning. It's used for what's called parameter optimization, which is basically finding parameters that minimize our cost function. I hope to explain what that all means in this video, so let's begin. So before getting into gradient descent, I thought I'd give you guys just a quick recap of linear regression. So in the previous episode, we had our data of temperature and humidity. We plotted the data, we saw that this followed roughly a linear relationship. We then wanted to find our regression line, and we did that by plotting our parameters against the cost function, and we found where the minimum cost was, which was here. And this gave the values of theta 0 and theta 1 for our regression line, which we then plotted on our data here. Now, gradient descent is essentially the means in which we obtain this minimum cost to obtain the values of theta 1 and theta 0, which we use in our regression line. And just to give an overview of gradient descent, we essentially initialize theta 1 and theta 0 to a random value, and then we apply an algorithm, which I'm going to be going through in this episode, which iterates and takes us down to the minimum point. To understand how the algorithm does this, we're going to look at gradient descent in two dimensions. This is where we have a regression line of y hat equals theta 1x. So before we had y hat equals theta 0 plus theta 1x. But now we're getting rid of the theta 0 and we're simply just setting theta 0 equals to 0 and just seeing how gradient descent will play out here. So again, similarly, we have our parameter theta 1 and our cost function j of theta 1, and our cost function is given by the following formula. Remember that this here is simply y hat. So the concept here is the same. We're summing the square errors and we're dividing this total sum by 2m. So gradient descent utilizes what's called the derivative of the cost function, which is given by the following formula. If you guys aren't too familiar with how to do derivatives in calculus, don't worry too much, but it's always good to know. Essentially, the derivative gives the slope of a function at any given point. Like let's say we wanted to figure out the slope of our function at the point of theta 1 equals 2. What we could do is put a point here and draw a straight line at a tangent, and we can calculate the gradient of this line to be minus 2 over 2, which is minus 1. Or we can use our derivative function here, and we simply plug in theta 1 as 2, and we get minus 1, which is a much more efficient way of calculating the slope of our function at any given point. And gradient descent essentially utilizes the derivative function to reach our minimum point here. How that is done, I will show you guys now. So the gradient descent algorithm with just one parameter has the following algorithm. We initiate theta 1 to 0, and we repeat until convergence. What that means is essentially we repeat until we find a minimum point. So what we're doing is we're updating theta 1 by setting it equal to the previous theta 1, which in this case would be 0. And then we update it by minus alpha times our derivative function. And alpha here is given by what's called our learning rates, which I'll be going through later. And dd theta 1 of our cost function was shown on the previous slide. So let's see how this algorithm plays out. We set alpha equals to 0.5, more on this later, and we initialize theta 1 equals to 0 as the first step of our algorithm. So that's shown here. Theta 1 is initialized at 0. And then let's go through a first iteration. It's found that the derivative of our cost function at theta 1, 0 is minus 2. And then we update our theta 1. So theta 1 is equal to 0, which was our initial parameter, minus alpha, which is 0.5, which we set at the start, times minus 2, which is our derivative function, which gives us 1. So that now moves theta 1 from 0 to 1. So we can see now that it's getting closer towards our minimum here. So let's go through a next iteration. So on the second iteration, we find that a derivative at theta equals 1 was minus 1.5. And then we update theta 1 by doing theta 1 equals 1. Remember, it was 1 from the previous iteration. And then we apply the formula. So we do minus alpha times this should be minus 1.5, sorry. It should be the value of this. And we get a value of 1.75. So theta 1 now moves to 1.75. So you can see that. So now it's getting even closer. So repeat this algorithm again and again until we do it n times and we reach our minimum. dd theta 1 of j 2.25 represents the previous, like the one before last iteration. And then we simply update theta 1 by setting it equal to 2.25, which was this value here, 2.25. And we subtract our alpha times our value of our derivative at 2.25 to give us 2.5, which is found to be our minimum. How do we know it's our minimum, and how does the algorithm know to stop here? It's because we said to repeat the algorithm until it converges. And because now it's reached a minimum point, it therefore has converged, so the algorithm stops. The way that the computer recognizes that it's converged is by doing a few extra iterations. So let's say, for instance, we go now beyond n and we do n plus 1. Because the derivative now at 2.5 is 0, our theta 1 value remains the same at 2.5. And if we try to keep iterating again to n plus 2, n plus 3, theta 1 will stay constant at 2.5. So we know we have reached our minimum point and our optimal solution for theta 1, which we then can go on to use in our regression line as y hat equals 2.5x. So in the previous slides, I mentioned something called the learning rate alpha, which I hope to go over now. So the learning rate alpha can be thought of as how quick we reach our minimum point in our cost function. If we set alpha to be very, very small, such as 0.0001, then that would mean that we update our value of theta 1, very slowly, because remember, we had our algorithm, gradient descent algorithm of theta 1 equals theta 1 minus alpha times d of d theta 1 of our cost function, j of theta 1. And if alpha is very, very small, then we're only going to be making small changes to theta 1 each time. So it will take quite a while to reach our minimum. This can take a lot of computing power and is inefficient. The positive thing about this is it's guaranteed not to miss our minimum point because it iterates, little bit by little bit until it reaches our minimum. If we set alpha to be too high, let's say for instance alpha is 10, we're going to be changing theta 1 by much more because we're going to be doing minus 10 times our function here. And theta 1 minus, a large number will change it significantly. The result of this is the value of theta 1 will be going everywhere. Be going from here to here to here to here, and hopefully it will be getting closer to our minimum, but it may actually miss it, and it may fluctuate between these 2 points and never reach our minimum, which may result in an inaccurate value for theta 1, which will result in an inaccurate model, which is something that none of us want. We usually choose a value of alpha to be equal to roughly 0.001, or we could go to alpha equals 1. Usually it's within this range, and the way that we can determine what alpha is best for our model is by simply experimenting. It's advised to start with alpha being 0.01 and then going by a factor of 10, so then trying alpha with 0.01 and then 0.1 and then 1 and seeing what works best within this range. And then let's say, for instance, we found that our computer found a minimum quite quickly and it was accurate between these two, and then we'll then try, for instance, 0.0015 and try to narrow down a good value for alpha there. It doesn't make a significant difference, but it definitely helps with computing power, and it's also important in some cases to keep alpha relatively low to ensure that the minimum value found is accurate. Let's now take a look at gradient descent in 3 dimensions, which is what we had in the initial case with both theta 1 and theta 0 and our cost function j theta 0 theta 1. And just as a side note, guys, gradient descent works on all cost functions and all shaped cost functions, and not just the one that I showed you guys with the temperature and humidity, but also like this one as well, where we have a sort of bowl shape. And the concept of gradient descent remains the same as in 2 dimensions, where we're just looking at theta 1 and j of theta 1, in the idea that we're updating theta 1 every time and using its derivatives. But now we're working in 3 dimensions. We have to use what's called partial derivatives in order to determine the slope relative to theta 1 and theta 0. So the cost function of j of theta 0 theta 1 is given by the following formula. Remember, y hat, our regression line, is theta 0 plus theta 1 x, which is shown here. So now we're going to be using what's called partial derivatives to update a value of theta 0 and theta 1, which are given by the following formulas. This essentially calculates the derivative of theta 0 relative to the theta 0 plane, and our second formula calculates the derivative of theta 1 relative to the theta 1 plane. So the concept is sort of the same as we had in 2 dimensions, in the idea that we use the idea that we use these derivative formulas to calculate the gradient of our cost function, but now we're doing it relative to two different planes. So both relative to the θ1 plane and θ0 plane. So in which case, if we were to, for instance, wanted to calculate the partial derivative of θ0 at any given point, let's say at 0, we could draw a line tangent to here and calculate the gradient of this line, or we can use our partial derivative function here, and the same applies for our partial derivative d θ1. We could technically draw a line, we could draw a point on our θ1 plane and try to figure out the gradient like this, or we can use our partial derivative formula, which is a lot quicker. So the partial derivatives essentially just give us the slope, of our cost function, but relative either to the θ0 plane or the θ1 plane. Let's now take a look at the algorithm, and you guys should be seeing some similarities as we had with just one parameter. So here we initiate θ0 and θ1 both to 0, and we repeat until convergence. Again, repeat until we reach a minimum point, or until θ0 and θ1 no longer change in value. And we update θ0, but this time using the partial derivative of θ0, and we update θ1 using this time the partial derivative of θ1. And the effect of this algorithm is the exact same as with one parameter, where we're just initializing both θ0 and θ1 to 0. So now they're both 0, so we look for 0, 0, which is roughly here. And then as we repeat our algorithm, repeat until convergence, as we repeat it, we make our way down to the minimum, which is given by the point roughly 2, 2. And then we use the values of θ1 is equal to 2 and θ0 is equal to 2 in our final regression line to give y hat equals 2 plus 2x. So just a note on initializing our parameters. As you guys may have noticed in all the previous gradient descent algorithms, we always initiated our parameters to be 0, but this may not actually be optimal, as for instance, if we had a cost function which looked like this and we wanted to apply gradient descent on it, if we initiate both of them to be at roughly 0, 0, so roughly up here somewhere, and we want to apply gradient descent, it might converge to a point here where it turns out that the partial derivatives of both d θ0 of our cost function, j of θ0, θ1 is equal to 0, and our partial derivative of θ1 of our cost function, j of θ0, θ1 is also equal to 0. So at this point here, our algorithm actually converges and would stop, but as we can see by looking at our graph, this isn't actually the minimum point. The minimum point can be found here, which would be a much more optimal solution for θ1 and θ0. So how do we prevent our algorithm from converging to a non-optimal point? Is that when we apply this algorithm, we actually set θ0 and θ1 not just to 0, 0, but to multiple different values such as 1, 3, or 2, 2, or anything like that, and we find which of these initializations resulted in the optimal cost, and we then use these final parameters in our final regression line, y hat equals θ0 plus θ1 x. This is a much safer option as it reduces the chances of our algorithm converging on a non-optimal point, which will help us produce more accurate models. It's just something to be aware of. When you guys do actually implement gradient descent in Python, it does all this parameter initialization and implements the gradient descent algorithm in a very efficient way. So you guys don't really have to worry about this. It's just a nice thing to know that not all cost functions are convergent. Not all cost functions have a single minimum. Some have what's called local minimum and global minimum, which can sometimes be a problem for our gradient descent algorithm. Let's now take a look at gradient descent in n dimensions. So previously with our example with temperature and humidity, we had simply one input x, and we're trying to map this onto our target value y, and we had a regression line of y hat equals θ0 plus θ1x, where we only have two parameters. So I'm just going to introduce a new concept to you guys. Sometimes we may not just have one input x, which we want to use to predict values for y. We can have several inputs x. For instance, not just humidity, but wind speed and pressure as well. And if this is the case, it's common convention to call each input column as x subscript 1 or x subscript 2 and x subscript 3. And we may want to use all of these input values to come up with a temperature y. In this case, we would have a linear regression line that would look something like this, where we have even more parameters and we're working with even more dimensions. So in this case, each input x is assigned its own parameter. This theta 0 plus theta 1, x1 which was exactly what we had on the previous slide, but now we're adding on theta 2, x2 and theta 3, x3. So how will we apply gradient descent when we have 3 or even 4 parameters? But this time we have a beast of a cost function with our y hat being, as before, theta 0 plus theta 1, x1 plus theta 2, x2 plus theta 3, x3, which is shown here in our cost function. Again, the concept is the same. We're summing the square errors and dividing it by the total number of examples. Before, when we were plotting our cost function in 2D and 3D, it was quite easy to visualize. For instance, with theta 1 and j theta 1, we had a graph that looked something like this, and we saw how gradient descent worked here. And then we went on to look at gradient descent in 3 dimensions, where we had a cost function that looked something like this. But now we have 4 parameters: theta 0, theta 1, theta 2, and theta 3. So it's very difficult to visualize in 5 dimensions, and it'll be difficult to see how, when we change each of these values, and how does that have an effect on our overall cost function. The thing is, we don't actually have to visualize it. We can just simply apply the gradient descent algorithm. So let's now take a look at the gradient descent algorithm, but this time with 4 parameters. Again, the concept remains exactly the same. We initialize all the parameters. In this case, we initialize it all to 0, and then we repeat the following algorithm until convergence. That is, we update theta 0 using its partial derivatives d of t theta 0, and then we do the same for theta 1, theta 2, and theta 3, and we keep repeating until eventually each parameter converges, and at that point we stop the algorithm, we read what values of theta 0, theta 1, theta 2, and theta 3 we have, and we use that in our final regression line. Y hat equals theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, and we then use this final regression line to come up with predictions for temperature. So it's very difficult to visualize how this algorithm would work if we had a cost function and all these parameters. So like I said, we don't have to visualize it, and the computer will find all the optimal values for us. So let's try to generalize this algorithm and see how it would work with not just 4, but perhaps 10 or even 100 parameters. So let's take a look at the gradient descent algorithm with n parameters. So for I number of parameters n, we set theta I equals to 0. Essentially, we're setting all the parameters in our regression line. Let's say, for instance, it was theta 0 plus theta 1, x1 plus plus theta n xn. We're setting all of these parameters to 0. In reality, like I said, it's a bit more complicated. We'd actually set all of these parameters to multiple values, not just 0, to prevent them converging on a local minima, which I explained as before. And then we would repeat the following algorithm until convergence. For I number of parameters n, we update each parameter theta I using the following gradient descent algorithm. So this is the exact same as we were looking at gradient descent in 2 dimensions and 3 dimensions with 1 parameter and 2 parameters respectively. This is the exact same as before, but essentially we're just looping through all the parameters and updating each one individually. So I hope after watching this video, gradient descent makes a bit more sense to you guys. A lot of the maths explained in this video is fairly complex, and even data scientists struggle to get their head around them. So don't worry if you didn't understand all the concepts explained. When it comes to implementing gradient descent in Python, we simply just have to call a function and it will do all of this for us. But it's nice to know what's going on in the background when we're calling these functions. So yeah, I hope that helps you guys understand gradient descent a bit better. In the next episode, we'll be going through linear regression and implementing it in Python. So we're going to get hands-on. So I hope to see you guys there.